In this episode, we take the same careful alignment mindset you have been building and apply it to the moment where data work becomes real infrastructure, which is the way data is ingested, stored, and kept up to date. Beginners often imagine data as something that simply exists in a spreadsheet or a database, but in real systems, data has to travel, it has to be shaped, and it has to be trusted along the way. If ingestion and storage are designed poorly, even a brilliant model cannot rescue the project because the inputs will be late, incomplete, inconsistent, or impossible to audit. The goal here is to help you think like a responsible builder by understanding why formats matter, why pipelines are more than plumbing, why lineage is how you defend your outputs, and why refresh cadence is not just scheduling, but an accuracy and risk decision. As we go, you will see that these choices are deeply connected to security in cloud environments, because data often includes sensitive signals and must be governed from the beginning. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A practical ingestion and storage design starts with a clear picture of what you are trying to preserve about the data, because different use cases demand different fidelity. Some projects need raw, detailed events so you can reconstruct sequences and investigate edge cases, while others only need aggregated features that support a stable business metric. If you only store aggregated summaries and later discover you need the raw context to explain a model output, you may find you cannot answer basic questions about why the system behaved as it did. On the other hand, storing everything forever can create cost and privacy risk that the business cannot accept, especially when logs include user identifiers and behavior traces. This is why good design begins with intentionality about granularity, retention, and access, rather than defaulting to either extreme. In cloud security analytics, a common example is deciding whether you need full event payloads or only normalized fields, because payloads can carry sensitive details that should not be widely accessible. The deeper point is that ingestion and storage are not neutral, because they encode your assumptions about what will matter later. A thoughtful design preserves enough detail to support your decisions and audits while respecting constraints. Data formats are one of the first visible choices, and they matter more than beginners expect because format influences how data is parsed, compressed, queried, and validated. A format is not just a file type. It is a contract about structure, data types, and how missing or nested values are represented. Some formats are good for human readability and interchange, while others are optimized for analytics performance, compression, and schema enforcement. The beginner trap is to treat format as an afterthought, like choosing whatever is convenient, and then later discovering that your queries are slow, your fields are inconsistent, or your storage costs are unnecessary. Format also affects how you represent complex records, such as cloud logs that include nested objects, arrays of attributes, and variable fields across services. If you flatten everything too early, you can lose meaning, but if you keep everything deeply nested without a plan, it can become difficult to query and validate. A sensible approach is to treat format as a tool chosen to match the access pattern, meaning how you plan to read and use the data. When you get that match right, ingestion becomes more reliable and downstream modeling becomes less painful. Schema decisions are tightly tied to format decisions, because schema is the way you define what fields exist, what types they have, and what values are valid. Beginners often learn that schema can be flexible, especially in log-style data, and flexibility sounds convenient until you realize it can hide silent data quality failures. If a field changes type from number to string, or if a field disappears from half the records after a service update, a flexible schema may accept the change without warning, and your features may quietly degrade. A strict schema can prevent bad data from entering your analytics layer, but it can also cause ingestion failures when upstream systems evolve. This tension is why many mature data platforms use layered schemas, where raw ingestion tolerates variability, but curated layers enforce consistency for analysis. In security monitoring, schema clarity is crucial because a field that appears to represent an action might actually represent a category, and misinterpretation can lead to wrong detection logic. Good schema design includes explicit handling of missingness, because missing values can mean unknown, not applicable, or not collected, and those meanings lead to different modeling interpretations. When you treat schema as a living contract instead of a static diagram, you design ingestion that can survive change. Pipelines are the pathways data follows from source to storage to downstream use, and they are best understood as systems that need to be reliable, observable, and testable. A pipeline can include collection, transport, parsing, validation, enrichment, deduplication, aggregation, and loading into storage, and each step introduces opportunities for errors. Beginners sometimes assume pipelines fail loudly, but many pipeline failures are silent, such as dropping records under load, misparsing a field, or delaying delivery so that time windows shift. The consequence is that your models and metrics can be wrong in a way that looks plausible, which is one of the most dangerous failure modes. Good pipeline design includes checks that measure completeness and timeliness, so you can detect when the pipeline is drifting away from expected behavior. In cloud environments, pipelines may cross accounts, regions, or services, and that increases the need for consistent identity mapping and timestamp handling. The most important mental model is that pipelines are part of your data product, not a background detail, because they directly shape what your model will learn and what your dashboards will claim. When a pipeline is well designed, it supports trust. An important ingestion choice is whether you are handling data in batches or as a stream, because this affects latency, cost, and the kinds of decisions you can support. Batch ingestion collects data over a period and loads it at intervals, which can be efficient and easier to manage, but it introduces delay that may not be acceptable for time-sensitive detection or response. Streaming ingestion delivers events continuously or near continuously, which can support real-time alerts, but it increases complexity because you must handle out-of-order events, duplicates, and partial failures while still producing coherent outputs. Beginners often assume streaming is always better because it sounds modern, but streaming is only valuable if the decision truly needs low latency and the organization can respond quickly enough to make that latency worthwhile. In many business settings, daily or hourly updates are sufficient, and the simplest reliable approach can outperform an overly complex real-time system that fails intermittently. In security monitoring, streaming can make sense for urgent response, but batch systems still play a vital role in retrospective analysis, investigations, and model retraining. A thoughtful design often uses both, with streaming for near-term signals and batch for durable history. Storage decisions are not only about where data sits, but about what kinds of questions you need to ask of it later. Some storage patterns are optimized for fast retrieval of recent events, while others are optimized for deep analytical queries over large histories. Beginners sometimes choose a storage approach based on what they have heard is popular, and then struggle when the workload does not match the storage strengths. You also need to consider whether the storage layer supports the kind of indexing, partitioning, and compression that your data requires, because that influences both cost and performance. For example, event data often benefits from time-based organization because most queries focus on recent windows or specific incidents. In cloud security contexts, storage choices are also governance choices, because storage determines who can access raw logs, how encryption and access controls are applied, and how audit trails are maintained. A good design separates raw storage, which preserves fidelity, from curated storage, which provides standardized, safe-to-use datasets for analysts and models. This separation allows you to enforce privacy constraints by limiting broad access to raw records while still enabling useful analysis. Storage is therefore part of risk management as much as it is part of performance. Partitioning and organization of data are practical details that determine whether your system behaves predictably at scale, and they should be chosen with intent rather than left to defaults. When you partition by time, by tenant, by region, or by some other dimension, you are choosing the natural slices of your data that will be efficient to query and manage. Without thoughtful partitioning, queries can become expensive because they must scan huge amounts of unrelated data, and retention management becomes harder because you cannot easily expire old partitions. Beginners often discover this only after the dataset grows, when a query that once took seconds now takes minutes, and the platform costs rise unexpectedly. In security analytics, partitioning also supports investigations because incidents are often scoped by time and environment, and you want to isolate the relevant slice quickly. Organization also helps with privacy because partition boundaries can align with access control boundaries, such as separating production from test or separating different business units. If you design partitions that align with governance, you reduce the risk of accidental overexposure. When partitioning aligns with your most common questions and your access model, storage becomes an enabler rather than a bottleneck. Lineage is the concept that lets you answer the question of where a data value came from and how it was transformed, and it is one of the most underrated foundations of trustworthy AI. When a model output is questioned, you need to be able to trace the inputs back through the pipeline to the original sources, along with the transformation steps that created the features. Without lineage, you cannot reliably debug, you cannot audit, and you cannot defend your results when stakeholders ask why the system flagged a case or why a metric changed. Beginners sometimes think lineage is only for compliance teams, but it is also for engineering sanity because it prevents you from guessing when something goes wrong. Lineage includes data source identifiers, transformation versions, timestamps, and links to code or configuration that perform the transformation. In cloud security settings, lineage can be crucial because signals often pass through multiple services and normalization layers, and a subtle parser change can shift meaning across millions of records. A well-designed lineage system makes changes visible and reversible because you can identify which derived tables and models were affected. Lineage is how you make your data pipeline accountable. Closely related to lineage is the idea of versioning, which applies not only to code but to data and schemas as well. If you change a parsing rule, alter a feature definition, or update a deduplication policy, you are effectively changing what the dataset means, even if the table name stays the same. Beginners sometimes overwrite datasets and then cannot reproduce results, which undermines trust and makes debugging nearly impossible. Versioning provides a controlled way to introduce changes while preserving the ability to compare old and new behaviors. In model-driven systems, versioning matters because a model trained on one data definition may behave differently when the definition changes, and you need to detect and manage that shift. Versioning also supports rollback, meaning you can revert to a known good pipeline configuration if a new change produces unexpected outcomes. In security analytics, where alert volumes and thresholds can affect operations, rollback capability is a safety feature. Treating data definitions as version artifacts is part of treating the whole system as engineered, not improvised. When you can track what changed and when, you can manage evolution without losing reliability. Refresh cadence is the schedule by which your datasets are updated, and it is one of the most important alignment decisions because it connects data engineering directly to decision value. If a dataset updates too slowly, decisions are made on stale information, which can reduce effectiveness and create false confidence. If a dataset updates too frequently without control, you can create churn where metrics jump around, models see unstable inputs, and stakeholders lose trust because the numbers do not settle. Beginners often assume faster refresh is always better, but cadence must match the decision cycle and the volatility of the underlying behavior. In cloud security, some signals are urgent and benefit from near real-time refresh, while others are stable and can be refreshed daily without loss of value. Cadence also interacts with cost, because more frequent updates can increase compute usage and storage churn. Another subtle point is that cadence affects evaluation, because if you evaluate a model on a dataset that is updated differently than the production feed, you can create mismatches that hide real performance issues. Thoughtful cadence design treats time as a first-class element of correctness. A refresh cadence decision is incomplete without an approach to late-arriving data and corrections, because real systems rarely deliver perfectly ordered, perfectly complete events. Logs can arrive late due to network issues, service outages, or buffering, and sometimes records are corrected after initial ingestion. If you ignore late arrivals, your aggregates and features may be wrong, especially for time-windowed metrics that depend on complete event sets. If you constantly rewrite history, your dashboards can shift unpredictably and your stakeholders may lose confidence because yesterday's numbers change today. The solution is not one universal rule but a deliberate policy, such as allowing a correction window for recent periods while freezing older periods, or distinguishing between provisional and finalized metrics. Beginners often discover this problem after a mismatch appears between two reports, and they try to patch it ad hoc, which leads to inconsistent logic across teams. In security analytics, late-arriving events can affect investigations and incident timelines, so you need a consistent approach that preserves evidentiary clarity. A thoughtful ingestion design includes explicit handling of lateness so your system remains coherent. Security, privacy, and access controls are woven through ingestion and storage decisions, because data pipelines often carry sensitive information across boundaries. In a cloud environment, data can cross accounts, regions, and vendors, and every hop is an opportunity for exposure if access is not designed carefully. Beginners sometimes think security is added after the data is stored, but the safest approach is to build controls into the pipeline, such as limiting who can access raw data, applying encryption, and ensuring that only curated, minimized datasets are broadly available. Access controls also support least privilege, which is the idea that users and services should have only the access they need to perform their role. Personally identifiable information, PII, is a special concern because it increases both privacy risk and compliance burden, and ingestion design should support minimization, masking, or tokenization where appropriate. Lineage and audit trails become part of security as well, because they allow you to demonstrate who accessed data and how it was used. When ingestion and storage design respects governance from the beginning, you reduce the chance of building a system that cannot be deployed or that creates unacceptable risk. Good data engineering is therefore part of cybersecurity, not separate from it. Finally, all of these choices should be tied back to the practical reality that data systems must be operated, monitored, and improved over time, not just built once. A pipeline that works today can fail tomorrow due to upstream changes, schema shifts, new services, or changes in workload volume. Storage costs can grow, query patterns can change, and compliance requirements can evolve, all of which means the ingestion and storage design must be maintainable and observable. Beginners sometimes focus only on the happy path where data flows perfectly, but the real skill is designing for failure modes, such as missing partitions, delayed feeds, and corrupted records, and ensuring you can detect and recover from them. Monitoring should track data freshness, completeness, and distribution changes, because these signals often warn you before models fail or dashboards become misleading. This operational perspective also helps with stakeholder trust, because you can explain how you know the system is healthy and what you do when it is not. In cloud security contexts, operational discipline is critical because bad data can lead to bad decisions quickly. A thoughtful design is one you can run reliably. Bringing everything together, designing ingestion and storage decisions, is about creating a trustworthy foundation that preserves meaning, supports the right access patterns, and respects governance constraints from the start. Formats and schemas define how data is represented and validated, and those choices determine whether downstream analysis is consistent or fragile. Pipelines define how data moves and transforms, and their reliability determines whether your models are learning from reality or from silent pipeline errors. Lineage and versioning provide accountability, making it possible to debug, audit, and explain how outputs were produced, especially when questions or disputes arise. Refresh cadence connects data engineering to decision value, because timeliness and stability must match the business cycle while handling late-arriving events coherently. When you design these elements thoughtfully, you avoid building impressive models on shaky ground, and you reduce the risk of privacy, compliance, and operational failures. This is the mindset that turns data work into a durable system, and it is exactly the kind of disciplined thinking that supports strong performance on the CompTIA DataAI certification and responsible behavior in real cloud security environments.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.